All right, let's finish up this section 2.1. Okay. Next on the menu is the definition of a basis norm. So for any basis of a vector space V, say V1 through V sub k, any linearly independent spanning set, for vector x in that vector space, say it can be written as the linear combination C1 V1 plus C2 V2 through C sub k V sub k. Of course, it can be uniquely represented as such if that's the basis, the V1 through V sub k. Unique representations needed because we're going to define something in terms of these coefficients, C1 through C sub k. They better be uniquely determined by the vector. So we're defining something called a basis norm, rho of x, to be the sum from 1 to k of these C sub j's squared, square root of. Okay, if we use the standard basis vector, we're getting the standard Euclidean norm behavior here. But this is defined in terms of any basis of a vector space, a subspace of Rn in our setting. And we need to go through and verify that this thing really is a norm. Okay, so we need the three properties. The third one was a triangle inequality, the one we'd anticipate having maybe the most trouble with. We've got Schwarz's inequality already, and we're not that far from Euclidean spaces and Euclidean norms in this stuff. So let's go through the proof that the basis norm is indeed a norm for any basis V1 through V sub k of a vector space, a subspace of Rn. All right. Okay, so take your vectors x and y, represent them with respect to this basis V1 through V sub k. Say x is C1 through C sub k times the respective basis vectors. Say y is V1 through D1 V1 through D sub k V sub k with coefficients D sub i's respectively on the V sub i's. If x is non-zero, then one of those C sub i's is non-zero. Remember, we're going to take the sum of the squares of those coefficients. Then you're going to have that the basis norm, rho of x, is positive as required. Certainly, if we put in the zero vector, all these coefficients would have to be zero, and so the basis norm would be zero. So part one, piece of cake. Part two, the definition of a norm was that the norm of ax equals the absolute value of a times the norm of x. Okay, we're using this rho symbol for norm. So when we take rho of ax, that would be rho of a. Here's x expressed in terms of those basis elements. We'll distribute. Here's ax expressed in terms of those basis elements. So if you want the basis norm of that, we'll take each of those coefficients, square them, add them together, take a square root. So we get a times c sub j, say, j equals 1 to k. So we're getting these things squared, square root of. Hey, we can bring the a squared constant outside of the summation. Evaluate the square root of a squared. That's where the absolute value comes from. What you're left with is just the c sub j squared. Why, that's the basis norm of the vector x that we started with by definition. Okay, so part two of the definition of norm is satisfied. Part three, triangle inequality. That's why we needed the two vectors, the x's and the y's. All right, so let's take rho of x plus y. Okay, everything's got to go back to the basis. So we'll write x in terms of the basis vectors, y in terms of the basis vectors. You skip a step of arithmetic. Combining those, we'll have first coefficient in the representation of x plus first coefficient in the representation of y times v sub 1, and so forth. So I skipped a step of arithmetic there. All right. Hey, we want a basis norm for this linear combination. Piece of cake. Take all the coefficients, square them, add them together. Normally we'd take a square root. Notice we're looking at the basis norm squared, so we'll take a square root later. Okay, so we don't get the square root because we've actually squared here and here. Multiply out, FOIL it, old-fashioned stuff. Break that sum up to give us this. All right, now I'm liking the looks of this. Sum from j equals 1 to k of c sub j squared. Why, that rings a bell. That's the basis norm of x. Here's the basis norm of y, by the way. Yeah, I got this thing in the middle in the way. Well, we've got Schwarz's inequality. After all, these are vectors and are in. In general, if there looks like we're in a k-dimensional space, but these are vectors and are in for some n. And so we can use Schwarz's inequality to say, hey, this is effectively an inner product of x and y. This inner product is less than or equal to the product of these two quantities here. And of course, these are basis norms for us. All right, so we've got, the way it's written here is we've got this quantity, sum from j equals 1 to k of c sub j squared, plus twice that quantity, square root of this other quantity. This is a perfect square, just like we had when we established a triangle inequality in Rn. All right, so you might want to view this as that square root squared, view this as that square root squared, and then we see that it factors as a perfect square. The quantities we're getting in that square are rho of x plus rho of y. So we've got rho of x plus y squared equals rho of x plus rho of y squared. Take square roots of both sides, and there's the triangle inequality. So indeed, this basis norm thing for any basis really is a norm thing. Okay. I'm going to define an equivalence relation on norms. And we're going to see in here, all norms on Rn turn out to be equivalent. Not equal, but equivalent in the following sense. Let's take two norms, let's denote them like norm sub A and norm sub B. Let these be norms on a given vector space V. Then norm sub A is said to be equivalent to norm sub B, denoted with these symbols here. Looks like a congruence symbol, following Gentle's notation. Just a regular tilde is a little more common for equivalence relations, but we'll get by. If there are positive R and S scalars, such that for every vector in the vector space, we have the norm, let's make that a little bit bigger, the B norm of x times r is less than or equal to the A norm of x is less than or equal to the B norm of x times s. So we've got this A norm of x sandwiched in a sense between these two B norms. Some constants, positive constants, r and s that establish this. This equivalence doesn't say that the values are the same. It's not a value of the norm in this equivalence sense. It really, what it deals with is topological properties of the vector spaces and congruence of sequences, as it says. We'll have the same open sets if we have a vector space under one norm or an equivalent norm. We'll have the same open sets. We'll have the same sequences converging if we have equivalent norms. Now, this equivalence of norms, in fact, is an equivalence relation, reflexive, symmetric, transitive, straightforward. Left is one of the exercises from this section. And we need, especially, we need the transitivity stuff in a claim we're going to make here in the near future. The future is now. Okay. Every norm on a finite dimensional vector space. Okay, I'm going to keep my eye out when we go through the proof of this of where we're using that finite dimensional stuff. Every norm on a finite dimensional vector space V is equivalent to a basis norm for some basis. By this transitivity we just mentioned, that means any two norms on a finite dimensional vector space are equivalent. We're going to take a particular base, well, arbitrary basis, and show that any norm is equivalent to the basis norm determined by that basis. Transitivity that will then apply to say, you grab any norm and any other norm, they're both equivalent to, give me a basis, that basis norm, and so are equivalent to each other. This doesn't happen in infinite dimensions. Yeah, let's go ahead and read that next little note before we look at the proof. This class is about finite dimensional vector spaces with real coefficients. So in a sense, we're kind of restrictive. This theorem, it ain't true if we go to infinite dimensional vector spaces. Not all norms are equivalent in infinite dimensional vector spaces. With that observed, I'm particularly interested in where we use the finite dimensional part in the proof. Okay, this one's a bit lengthy, so I might even want to bounce around a little bit. All right, we're trying to show equivalence of norms. So we're looking for those parameters R and S that'll allow us to sandwich one of the norms between the other norm with those R's and S's introduced. We'll jump back and look at the definition here in a little while. Okay, so take an A norm, just any norm on this vector space, and take a basis, any basis on that vector space, say V1 through V sub k. All right. If we take X as a vector from the space, we know it can be written as a linear combination of the V1 through V sub k. Hey, the V1 through V sub k are given to be a basis, so X has this type of representation. All right. We're going for getting the A norm of X bounded between the basis norm, we'll indicate with a row, above and below, with those scalar multiples R and S introduced. Okay, so that's the plan. Well, we'll take the A norm of X. By definition, that's the A norm of. We've got X represented like this. Norms. If this A norm really is a norm, then triangle inequality holds, and the other properties of a norm. We can break this up using the triangle inequality and that behavior about scalar multiples to say that whatever this norm is less than or equal to the sum from 1 to k of absolute value of coefficients times norms of the V sub i's. Okay. Now I want to get a bound on this as well. Here's one way to do it. Let's treat this as an inner product of two vectors from, I guess we're in RK. Right? These vectors seem to have a basis with k elements, and so we're taking vectors from RK. We've got k coefficients, we've got k basis vectors. So let's consider the vectors from RK of absolute value of C1, absolute value of C2, up to absolute value of C sub k. Norm, A norm of V1, A norm of V2, up through A norm of V sub k. All right, so I want to look at those vectors because if we took the inner product of these two vectors, we'd have this times this, plus second one times second one, plus up through the last one times the last one. Adding those up, we'd have exactly this thing here. So we'd have a dot product of these two vectors. But you know, by Schwarz's inequality, how to get a bound on a dot product of two vectors in RK. That dot product, that inner product, is less than or equal to the Euclidean norm in RK on that first vector, this vector with the absolute values on it, sum from 1 to k, absolute value of C sub I squared, square root of, we don't really need the absolute values, we're dealing with real numbers here, so the squaring will make everything positive. And over here with the norms, the Euclidean norm in RK of this vector would be sum of the squares of the components, sum of the squares of the components, square root of. Okay, so we've got, remember where we're going with this, we've got the A norm of X less than or equal to this thing here. All right. Remember how we define a basis norm. What is the basis norm of vector X? We'd take these coefficients, square them, add them together, and take a square root. That's how a basis norm was defined. That's exactly what we got right here. This thing with the C sub i's in it, that's the basis norm of x with respect to the basis v1 through v sub k. We're denoting that basis norm as rho. Here's rho of x. So what we have is a norm of x is less than or equal to this quantity, which is this quantity, which is less than or equal to this, which is rho of x, times this. This is, you're going to like this part, this is some constant determined by the basis, but it's a constant. So other things may change, coefficients may change, the basis doesn't. This is a constant determined by the basis. All right, next slide will say a norm of x is less than or equal to rho of x times this thing here. A norm of x is less than or equal to rho of x times this thing here. Let's call this thing here S tilde. So S tilde is taken to be the sum from 1 to k of the a norms of those basis vectors squared square root of. All right, how y'all doing? Let's see, let's jump back to the notes. We've got the a norm of x is less than or equal to some constant times the basis norm, rho of x. I think that's halfway there. Let's look at the notes again. Okay, what did it mean for norms to be equivalent? It meant the a norm of x is less than or equal to some constant times the b norm of x. Well, that's exactly what we've got, except instead of s, we have s tilde. And instead of a b norm, we've got the basis norm, the rho of x thing. So we're halfway there. We've got this. We just need to get the other part. So that's where we are. Here's where we're going. All right. Now, let's come back to this part. I think I want to do the linear algebra first and some of these details later. Okay, we're going to consider a particular set. It's the surface of the closed unit ball in some space. I'm going to do some epsilon delta stuff. Gentle makes some claims that I'd like to go through the details on because I don't think they are very obvious. But more of that here in a little while. What we're going to do is find, moderately computationally, an R tilde. We're looking on the other side of that inequality now. We're going to find an R tilde, and that R tilde is going to satisfy, let's see, a norm of x. We got an equality over here. There's the rho of x stuff. We've got an equality here. We wanted to actually, that would work if this is a constant, but it maybe isn't. We're going to find an R tilde, and we're going to get a norm of x is greater than or equal to R tilde rho of x. Maybe more appropriately, R tilde rho of x is less than or equal to the a norm of x. So here's that R value, here's that S value, and in the definition of equivalence of norms, this is the B norm, the rho of x, and this is a B norm. So that's the plan. If we can find R, we've already found S, if we can find R tilde, such that we get this inequality satisfied, then we're good to go to say those norms are equivalent. Oh yeah, and the equivalence relation and the transitivity will then imply that any two norms on this vector space are equivalent. So that's the plan. We're looking for R tilde to get this inequality satisfied. So let me back up a few pages. Okay, it's, yeah, all right, so here's where we left off. We got the S tilde, we're good to go on that part. A norm of x is less than or equal to S tilde times the other norm of x. All right, So shifting gears a little bit, finding the R tilde is way harder. Let's see B, all X linear combinations of the V sub i's where the sum from I equals 1 to K of those coefficients, those U sub i's squared, absolute value, equals 1. Okay. This would be, the fact that we're considering vectors. It looks like those vectors have norm 1, but we got a bunch of norms floating around. They do have norm 1. In fact, they've got, here it is, they've got basis norm 1. We took the coefficients, squared them. I guess the absolute value isn't necessary because everything's real. But we took the coefficients, we squared them, added them up, arguably took a square root and got 1. Of course, got 1 without taking the square root. Same thing. Okay, so what we have here is actually it's the surface of the unit sphere in this vector space. And when I say unit sphere, that depends how you measure distances. We're measuring distances with a basis norm. It's all X and V that have a basis norm of 1. That's just the unit sphere. In RK under basis norm rho. Okay. Gentle states that C is obviously closed, that is topologically closed. Let's do a little bit of epsilon and delta stuff and show that. So I'm going to give a proof that C is topologically closed by showing that its complement is open. Okay, so take something in the complement, call it X, stepping aside from the notation with an X that we started with, and just let X be some vector that's not in this set C. It's in the complement of that set. All right, we're going to find an epsilon. We're going to use this epsilon right here. Let's take epsilon equals the absolute value of 1 minus rho of X. Rho of X being the basis norm of this new vector X. All right, consider the open ball of all vectors in V such that rho of V minus X is less than epsilon. All right, now with these norms, you're thinking about using them as distances, as a metric. And we'll actually do that more explicitly here before this section's over with. So what we're doing is trying to show that V minus C, the complement of C, is an open set. We're taking a point in that allegedly open set, and we're drawing an epsilon ball around it. We're looking at all points, all vectors V, that are within epsilon of X, measuring the distance using this basis norm rho. Claim is this open C, and here's why that's the case. Take Y, an element of C. We're going to show Y is further away from X than epsilon. Y, rho of Y minus X, the distance from Y to X, was greater than rho minus Y, rho of Y minus rho of X, or rho of X minus rho of Y. One of those is negative, depends on the relative sizes of these. By the way, that's just a little consequence of the triangle inequality. The norm of the difference is greater than the difference of the norms. I think that's the first time we've encountered that in here, but it's the consequence of the triangle inequality. Okay, well, what is rho of Y minus rho of X and the other way around? Well, we chose Y to be some vector on C. The vectors on C are those that have a rho value of 1, a basis norm of 1. So the rho of Y will be 1. So we get 1 minus rho of X here, or rho of X minus 1 down here. And of course, this is greater than or equal to both of these by the triangle inequality. Ultimately, I mean, one is uninteresting because one of them is negative. It depends on the rho values. If rho of X is less than 1, then we've got 1 minus rho of X equal to epsilon. Remember, epsilon is 1 minus rho of X absolute value of. Okay, if rho of X is less than 1, then 1 minus rho of X absolute value of is 1 minus rho of X. If rho of X is greater than 1, then 1 minus rho of X is negative. The absolute value would introduce another negative. In both cases, we get epsilon here. So if we take any point on C, the distance between that point and this given point X, greater than or equal to epsilon. In other words, this little open ball vectors within a distance of epsilon of X contains no elements of C. X was an arbitrary element of V minus C. That's the very definition, using a metric, of an open set. So indeed, V minus C is open. So its complement, C itself, is closed. Just an epsilon argument ultimately showing closure. A common way to show closure is by showing complements are open. Okay. So the set C is a closed set. Is it a bounded set? It's just a unit ball. You know some stuff about closed and bounded sets, I think. You know that about closed and bounded sets in certain settings. More of that in a second. Okay, so we're going to define a function f, mapping this closed and bounded set C into the real numbers by defining f of u to be the A norm of this vector u, which has this particular linear combination representation in terms of the basis vectors. So here's the mapping. Notice, indeed, this takes in, we have to put on the condition that these be unit vectors with respect to the row norm for the mapping to have the appropriate domain. The codomain is the reals. Yeah, it's a norm. Actually, it gives out vectors that are what? Gives out norms. So it gives out real numbers that are greater than or equal to 0. Of course, we don't get negative numbers out of this function f. But legitimate, its codomain is the reals. Its range involves non-negative real numbers. I mean, it might be capped somewhere. I don't know. I suspect it is, actually. All right. General claims this is a continuous mapping. Okay. Let's go through and establish that. Norms. When I define functions using norms, they're going to be continuous. No, you don't show that in sophomore linear algebra. Outside chance you show it in a senior level analysis. When I've taught it, we never quite went there. The claim is true, but let's go through a little proof of that as well. So these are the proofs I wanted to step aside and look at. All right, continuity, eh? Okay, that's what's an epsilon delta thing. Okay, so let epsilon be greater than 0. Pick you a point, let's call it y, to be in the domain of that function. So it's an element of C. That is, that vector will be a linear combination of the v sub I. There's some constraints on the u sub I in terms of getting this to be a vector y with the basis norm rho equal to 1. So the sums of the u sub I squares will have to equal 1. It's implicit in this somewhere. I don't think we ever actually use that, but that's implied given the mapping. Okay. We need to find a delta. I say, let's take delta equal to epsilon. Usual epsilon delta thing. You let epsilon be greater than 0. Somehow or other you find a delta. I say that's going to be how we're going to find the delta. And then you show when x is sufficiently close to y, that is, when the distance is less than delta, then the function values are within epsilon of each other. So the greatest hits of this slide are epsilon's greater than 0. We've chosen a delta. We've made the input values, x and y, sufficiently close together. Their distance apart is less than delta. We're measuring distance using the A norm for the inputs. The outputs are real numbers, so we're measuring distances there, just using the absolute value, where you measure distance in the reals. Inputs are sufficiently close together, less than delta. Outputs can be made within epsilon of each other as a result. This is sort of the arbitrarily close part, and the informal idea of arbitrarily close when sufficiently close. Okay, so we'll take x, let's represent it as u sub I prime, v sub I, let that be an element of the domain of the function. Some constraints, the sums of the use of I prime squared must equal 1 for this thing to lie on C as well. Anyhow, that doesn't come up, just the nearness matters. And we want to take this x to be within delta of y when measured with respect to the A norm. Okay, want to use the A norm because f of a vector is defined as its A norm. All right, well, we got epsilon equals delta. You know, delta is greater than the A norm of the difference, which in turn is greater than or equal to the difference of the A norms. Same trick we had on the previous page. One of these is positive and one is negative. So I can't tell you which is which, unless you'll tell me more about X and Y. We could express those, if you like, in terms of their linear combinations. We don't actually need that so much beyond recognizing when we do so, then that gives us f of y. Here's f of y. Here's f of x in terms of the representations, exactly from how we define the f function. Okay, so we get f of y minus f of x, or is it f of x minus f of y? It depends on the relative sizes, as we did on the previous page. We get the absolute value out of one or the other. It depends on the relative sizes of the f of x's and the f of y's. So what you get from this is epsilon is greater than the absolute value of, say, f of y minus f of x, or the other one. So if we have y minus x within delta of each other, then we have f of y minus f of x within epsilon of each other, the distance from f of y to f of x. That's totally epsilon delta definition of continuity. The setting is exotic. You measure distances differently because you're in different places. Other than that, it's just calculus 1 definition of continuity. But a little exotic. I mean, you measure distance on the input using the A norm and on the output using absolute value. That you didn't do in calculus 1, but conceptually it's the same thing. All right, so how we doing, y'all? We got the set C is a closed set, and the function f is defined here as a continuous function. All right, what do you know about continuous function as applied to closed sets? Does a continuous function map a closed set to a closed set? Anyone? Not necessarily. But we got a closed and bounded set. Closed and bounded sets are compact, right? Heine-Borel says a set is compact if and only if it's closed and bounded. No, Heine-Borel says a set, let's go at it a handful of different ways. In your senior level analysis class, you probably studied R1. You may have done some things in higher dimensions, but probably mostly one real value and a function with one real output. Functions that map the reals to the reals, for example. And in the topology of the real lines, you probably said, Heine-Borel says the following: a set of real numbers is compact if and only if it's closed and bounded. It's also true that in Rn, a set is compact if and only if it's closed and bounded in Rn. But there's other places that we can talk about closedness and boundedness where I can give you a closed and bounded set that is not compact. So Heine-Borel doesn't say everywhere compact and closed and bounded are the same. It says, if you let me be a little informal, it says in finite dimensions, compact and closed and bounded are the same. Remember, I was making a big deal about the finite dimension stuff and I wanted to see where we used it. This is it. So this result we're working on isn't even true in infinite dimensional spaces. And where this proof falls apart, I mean, we've been so far so good, everything was true above until we get here. We want to apply that continuous function f to that compact set C. We'll get out then a compact set of real numbers. That compact set in the real number setting will be closed and bounded. So it'll have a smallest value and it'll have a largest value because it's a closed and bounded set. That's where this falls apart if we were in infinite dimensions. So I won't necessarily have this minimum that we're about to use. All right, but in finite dimensions, where we are and where we will remain, though I love the infinite dimensional stuff, Heine-Borel will tell us, yeah, we've got a continuous image of a closed and bounded set that is a continuous image of a compact set. Then that image is also compact. That image is also closed and bounded because we're in finite dimensions. That means, okay, let's see, the image is actually a set of real numbers. That means this continuous function will have a maximum and a minimum value on that set C. So it does have an upper bound. We've already taken care of the upper bound without getting into all this compact set and continuity stuff. Also, remember, F was defined as a norm. It's defined as the A norm of input vectors. And we're saying there's a minimum. Let's call that minimum F of U sub star. So somewhere it attains its minimum, just calling that place U sub star. And F of U sub star is less than or equal to F of U for all U in that unit disk, that unit ball. That's set C. We're going to go further and say F of U star is actually greater than 0. Remember, the big picture is I'm looking for that value R tilde, and that's going to be it. Well, how do you know that minimum isn't 0? It's a norm. Norms can be 0. Yeah, but norms are only 0 when you put in 0 vectors. You didn't put in the 0 vector. You put in a vector of norm 1. Remember that part? That's what set C was. All right, so there exists a minimum. Why is that? Heine-Borel compact sets. That's why. And we're mapped into the real number, so max and min makes sense. I couldn't talk about, the extreme value theorem if this mapped us into R2 because we don't have that kind of ordering on R2. We do on the reals, though. The reals are a complete ordered field. So we're using the order and the closeness to get a minimum value out. So it has a minimum value. It attains that value. Speaking of extreme value theorem, in Calculus 1, you'll say a continuous function on a closed and bounded interval, A to B, attains a maximum and attains a minimum. That's the extreme value theorem. Yeah, same idea here. In senior level analysis, you'd replace closed and bounded interval with compact set. So if I have a compact set and a continuous function that gives out real numbers, maps it into the real numbers, then you'll have a maximum and a minimum. That's the extreme value theorem, and it's fairly general in a general setting. So we got a minimum, and that minimum is positive. The only way we could get 0 out of that function was to have a norm be 0. The only time that happens is when you put in the 0 vector. You didn't put in the 0 vector. You put in a vector with a norm of 1. Okay, so whatever this norm is, it's greater than 0. All right, call that R tilde. Okay, so let's see, we're getting to where we looked at the rest of this. Now we're going to take X, an arbitrary vector other than the 0 vector. So we're going to do some division down here. Then, if you look at the A norm of X, all right, here's X. That'd be the A norm of this thing here. How do you calculate A norms? Whoops, not just yet. Let's rewrite this in this weird, funky way here. Let's divide each of those scalars, C sub I, by this constant here. Sum from j equals 1 to k, C sub j squared, square root of. This is what? It's the basis norm of vector x, ain't it? Which is not 0. That's why the assumed x is not 0. All right, you do that if you'll balance the books. So look at it as taking this inside that norm. This is non-negative, so we can take it inside the norm without changing anything. We can distribute, get cancellation, and sure enough, this big, long, complicated thing simplifies down to just this previous thing. We do have an equality. All right. Yeah, what I say this was? The basis norm of this vector x. Okay, that'd be rho of x. What's this thing here? I don't know, let's call it f of c tilde. F took a norms of vectors. So whatever vector this is, call it c tilde. It's actually, we're about to introduce these words. It's a normalized version of vector x. But this is f of something because the f function was the a norm of vectors. Okay, call this vector c tilde. Oh, by the way, so we're taking c tilde to be that vector. If you'll go through and calculate rho of c tilde, the basis norm of the c tilde, you find out that it equals 1. I mean, you sum the coefficients squared, and sure enough, you get out 1. So you get this quantity over itself. So this really is, c tilde really is an element of C. All right. Is it independent of anything but the basis? No, it's got these C sub i's in them, and they depend on vector x. We need something that only involves the basis. Like with the S tilde, it only involved properties of the basis elements, V1 through V sub k. This doesn't. This involves these C's, and they're determined by vector x somehow or other. All right. We're trying to get out, right? The a norm of x is greater than or equal to r tilde times rho of x, where r tilde is a constant. Here's your problem. That ain't a constant. We were talking about an r tilde a second ago. How big could f of c tilde be when c tilde is on c? Or how little could it be, I guess? Well, I know f of u star is less than or equal to f of u whenever u is in this set C. So this f of u star is smaller than this or equal to this. And that's what we call the r tilde. So we're going to take this minimality of f of u star and get that as a lower bound. We wanted a lower bound, right? We're trying to get the a norm of x is greater than or equal to rho of x times some constant. There's the constant we're going to use. Okay. R tilde is where that minimum is what that minimum is. So f of c tilde greater than or equal to r tilde. Substitute in upstairs, we get the a norm of x is greater than or equal to r tilde rho of x, provided x was non-zero. Of course, if x equals 0, that's certainly true, because both those norms are 0. So we get equality there, but that was a loose end. And what we've established is, finally, r tilde rho of x is less than or equal to the a norm of x, which in turn is less than or equal to s tilde rho of x. The r tilde was some constant. It depended only on the basis elements. We didn't have a real tangible grasp on r tilde because it came out of theory stuff. It came out of the Heine-Borel theorem and these ideas of involving compact sets. But it didn't involve any of the C sub i's. All right, that means a tilde is equivalent to rho. These two norms are equivalent, and as we remarked earlier, that implies in finite dimensions, all norms on vector spaces are equivalent. All right. So that was something else, and you see exactly where we use the finite dimensional stuff. Okay, let's see. Last few things, we're going to move from norms to metrics here. I mean, we were arguably using norms as metrics in that previous thing. But if we've got norms, we effectively have a way to measure distance. When you measure distance, it's usually not called a norm, it's called a metric. More of that in a second. But if we have a sequence of vectors, x1, x2, and so forth, an infinite sequence, in some normed vector space, V, say we denote the norm usual way, which is a double absolute value bars. This sequence converges to vector x if, for all epsilon greater than 0, there's a capital M, a natural number, such that when the index is greater than or equal to M, then x minus x sub n is less than epsilon. This was a definition of converges, and of course this value x is called a limit. This is what that sequence converges to. Calculus 2 stuff. except instead of using absolute values, we're using norms to measure distance. No surprise, you just saw some pretty involved stuff where we were doing exactly that with epsilons and other things. Here we're talking sequences. It's not an epsilon delta, it's an epsilon capital M. Sometimes I use capital N down here, but I'm following Gentle's notation on this. All right, so if we have a norm, we can talk about convergence of sequences. We can normalize vectors. In fact, when we dealt with that C tilde thing, we had normalized vector X. So formally, this is what normalizing a vector is. You're familiar with this from sophomore linear algebra. You use it a bunch in the Gram-Schmidt process, looking for orthonormal bases. For non-zero vector X in a norm linear vector space, the vector X tilde, X divided by its norm, is a normalized vector associated with X. It's usually called a unit vector. Looks like Gentle is leaning towards tildes to indicate unit vectors in his manipulations. Of course, it had to be a non-zero vector to avoid the division by zero thing. So normalizing vectors is a common thing. Hey, what is a vector in Rn? Yeah, I'm kind of thinking magnitude and direction. The norm gives you an idea of the magnitude, and for direction, direction never takes a formal definition, but it's kind of an informal thought that the direction of this vector, I'll take this vector and just normalize it. It gives me a little unit vector that points in some direction. Not rigorous, but not at all a bad way to think as long as you're in Rn. And in sophomore linear algebra, you're almost exclusively in Rn. And in here, I think we are exclusively in Rn, unless I wander off on something that catches my fancy in infinite dimensions. Metric, you should be familiar with metrics from your undergraduate days. If S is any set of elements, delta, mapping this set of elements into R is called a metric. If for any elements X, Y, and Z, we have the following. Delta of XY is greater than 0 if X and Y are different, and delta of XY equals 0 if and only if X equals Y. Delta of XY equals delta of YX. Delta of XY is less than or equal to delta of X comma Z plus delta of Z comma Y. Delta for distance. The distance from X to Y is positive unless X equals Y, in which case that distance is 0. The distance from X to Y is the same as the distance from Y to X, the symmetry to it, and this is a triangle inequality. So this is a wee bit different from what we had. This metric stuff is a function that maps elements of a set. Sorry, this is a function that maps pairs of elements of this set into the reals. So actually, technically, it maps S cross S. It maps, so I need to correct that. It should say S times S. It maps ordered pairs of elements of S into the real numbers. Actually, we see from the first part, it maps it into the non-negative real numbers. Now, we can think of this norm as a length, but norms take individual vectors. They don't take pairs of vectors like the metric does. In this idea of a vector has magnitude and direction, you're good to go anywhere with a magnitude part if you've got a norm. So the norm does give the magnitude. Whereas this delta thing, this metric, gives you an idea of measuring distance. We can relate the two first with this formula. If you've got a norm, you can define a metric. Delta of xy is the norm of x minus y. That's how we were using it in those proofs. We took an A norm of x minus y somewhere in those computations. You won't go the other way around. We could use a metric to define a norm as given here. We'll just measure the distance of a vector from the zero vector, and that'll give a norm. Exercise 2.7, or a modified version of it, has you establishing exactly that. If you have a vector space, then you can use a norm to define a metric, or you can use a metric to define a norm. Vector space, you need to have the concept of a zero vector to go in that direction. And you got all that in a vector space. A little bit more geometric ideas. It's, I think it's the next section or the section after that. Somewhere in chapter 2, we're going to go through and try to draw a few more pictures in these things. Totally legitimate pictures, as long as we're in Rn. And you even go into higher dimensions. You go into infinite dimensions. If you're in a good infinite dimensional space, that's where applied math is done. Those Banach and Hilbert spaces I mentioned earlier, good infinite dimensional spaces. A lot of the geometry comes along for the ride. And a lot of the geometric ideas we'll have from Rn are valid in infinite dimensional spaces, the good ones at least. This is very geometric here, taking two vectors v1 and v2 in a vector space with an inner product. They're said to be orthogonal if that inner product is 0. In some sense, that was the real reason for introducing inner products. And it's possible to have norms without having inner products. There are normed vector spaces that don't have inner products on them. But if you have an inner product, you definitely have a norm. And this is more exotic setting stuff, not our Rn things. But orthogonality means the inner product is 0, just like the dot product was 0 in sophomore level linear algebra. A whole set of vectors, v1 through v sub k, is called an orthonormal set. If we take any v sub I, v sub j in that set, the inner product is 0 when I and j are different, and the inner product's 1 when I and j are the same. So any two vectors are perpendicular to each other. Any two different vectors are perpendicular to each other. And if j equals I, we have v sub I, inner product v sub I. That'd be the norm squared of v sub I equals 1. So normal for the orthogonality relationship. Ortho for the orthogonality part. Normal for the normalization, the fact that we got a bunch of unit vectors here. So an orthonormal set is a collection of vectors that are all unit vectors, vectors of length 1, which are pairwise perpendicular. Hey, this sounds familiar from sophomore linear algebra. So the proof is not hard. Nothing like that last one. Theorem 11 says a set of non-zero vectors, v1 through v sub k, in a vector space with an inner product, for which v sub I, v sub j, inner product equals 0 for I not equal j. So those vectors are, as I say, mutually orthogonal, is a linearly independent set. So you take non-zero vectors, you get the pairwise orthogonal, mutually orthogonal property, then you got a linearly independent set. Let's look at the proof of that one. Okay, linearly independent, we'll have to produce a linear combination, set equal to 0, and deduce that the coefficients must be 0. Definition of linearly independent. Okay, so let this be your mutually orthogonal set of vectors, v sub 1 through v sub k. Assume, we're going for a contradiction here, that the set is not linearly independent. All right, then there's a dependence relation, a1 v1 up through a sub k v sub k equals 0, where not all of these coefficients are 0 because we're assuming not linearly independent. Say it's a sub I that's non-zero. Okay, then let's move everything else to the other side of the equation and divide by a sub I. You can do that because a sub I is non-zero. Then you'll get v sub I actually is a linear combination of the others. All right, so we get v sub I is, we picked up all those negative signs from moving things to the other side, and we've divided each of the coefficients by the a sub I to produce this. Okay, let's take the inner product of v with itself. Okay, that'd be the norm squared of v sub I, more of that in a second. We've got v sub I represented like this, so let's take that representation for the first entry in that inner product. Okay, and we'll leave the second one the way it is. You know, properties of inner products. We can use linearity to get this v sub I in an inner product with v sub 1 and with v sub 2 and so forth. All right, notice what we've got here in the summation. I should probably point out It goes v1, v2 up through v sub I minus 1, jumps over v sub I to v sub I plus 1. Right, the v sub I is missing on the right-hand side because we've got it on the left-hand side. Okay, so let's use linearity. And linearity allows us to get an inner product of v1 with v sub I, v2 with v sub I minus 1 with v sub I plus 1 with v sub I up through v sub k with v sub I. But wait, we assumed all those vectors were orthogonal to each other. So all those inner products are 0. You got a bunch of 0 vectors. You got a bunch of 0 scalars here. So we're doing inner products. So we get the 0 scalar out. Hey, that means the norm squared of v sub I is 0. That means v sub I is a 0 vector. But we said this is a set of non-zero vectors. There's the contradiction. So the assumption was false. The assumption was, so stick with me there, not linearly independent. So that assumption is false, and these vectors, in fact, are linearly independent, and that's what the claim was. You do a pretty similar argument in sophomore linear algebra, since all you need to know is properties of, in sophomore linear algebra, properties of dot products. Back to the notes, we're getting there. Something that will be very geometric. This pops up when you do the Gram-Schmidt process in sophomore linear algebra, probably around the end of sophomore linear algebra. Two spaces of n vectors, v sub 1 and v sub 2, are said to be orthogonal, denoted v1 is orthogonal to v sub 2, if the inner product of v1 and v2 is 0 for every v1 vector in space capital V1 vector space and every v2 vector in capital V2 vector space. So I take anything from one vector space, inner product with anything from the other vector space, and we always get out 0 for the inner product. So every vector in V1 is orthogonal to every vector in V2. If V1 is orthogonal to V2 and V1 is a direct sum of V2 equals Rn, then V2 is called an orthogonal complement to V sub 1, denoted with this little perp exponent looking thing. It's called a perp space. V2 is the perp space of V1. That's how we read this little equation here. We only had direct sums defined when the intersection of those two vector spaces only consisted of the 0 vector. Yeah, that's the case. It should be addressed. It's addressed, I guess, in exercise 2.9. So this direct sum really is defined up here. And you've dealt with orthogonal complements probably in near when you dealt with the Gram-Schmidt process. The Gram-Schmidt process, in a sense, you're building up orthogonal complements as you go, applying that process. How about some bases of these things? Well, the arithmetic is nice, the dimensions are nice. If B1 is a basis for vector space V1 and B2 is a basis for vector space V2, where V1 and V2 are orthogonal vector spaces, need them to be finite dimensional because we're going to do some addition down here. We don't want to do addition with infinite cardinals on here. Claim is the union of those bases is a basis for the direct sum of those two vector spaces. This is established in one of the exercises as well. The dimension of the direct sum then would be, I'm not sure we've actually formally defined dimension yet, but you know it from sophomore linear algebra. We've done so much stuff already. Forget if we define dimension. No, we define basis at least. The cardinality of B1 union B2 equals the cardinality of B1 plus the cardinality of B2. It's argued up here that those sets are disjoint. Then the dimension of the direct sum is the sum of the dimensions. Not necessarily true if I replace direct sum with just regular old vector space sum. In some sense, regular old vector space sum was valid for any vector spaces, subspaces of a common vector space Rn. but there could have been some overlap in those two. And we didn't get this neat kind of addition of dimensions unless we have direct sums. And finally, a little bit of stuff on statistics related methods of keeping up with information using vectors. We introduced a one vector in Rn. Here I want to treat it as a column vector. I think earlier we maybe had treated it as a row vector. Doesn't really matter until it's time for us to actually use it. So here we're treating 1 sub n as a column vector. Turns out it's the transpose of it we're going to need. So we'll need to treat ultimately the vector in the inner product down here in terms of a row vector. But we've introduced this vector of all ones. We called it the summing vector. I think it was earlier in this section. It's a long section. If we take any vector in Rn, if we'll look at 1 sub n transpose, so 1 sub n transpose would be, cover this up, would be the vector, the row vector 1, 1, 1, 1, 1, be a 1 by n vector. So we'll take 1 sub n transpose, a 1 by n matrix, treat that row vector as a 1 by n matrix, treat this vector x in Rn as a column vector, so it's an n by 1 matrix. So if I want to multiply these two together, I really can, because the n dimension here is the same as the n dimension here, so the product exists as a matrix product. That matrix product would then be, or if you like, it's really just a dot product. It leads us to sum these things. And that's the reason it's called a summing vector. We'll take 1n transpose, that'd be 1, 1, 1, 1, 1 times x, column vector, x1, x2, x3, x sub n. What we get by doing that computation would be a sum of those x sub i's. All right, if you're treating this really as a matrix product, then technically this right-hand side is a 1 by 1 matrix instead of a scalar. And we're probably going to muddle the distinctions between a scalar and a 1 by 1 matrix. But then we could also treat this, in fact, as an inner product if we dealt with things in the appropriate ways. But that's the reason the one vector is called a summing vector. More formally, might want to do some things with arithmetic means and a mean vector. If x is a vector in Rn, the arithmetic mean, or simply the mean, x bar is defined as 1 over n times this little product we had upstairs. Hey, x bar is the sum of the x sub i's divided by n. Yeah, that should be the mean, right? The mean vector is, this angers me a little bit, Gentle, the author of the book, also denotes it as x bar. So is x bar the mean, the scalar, or x bar the mean vector being defined here? And then hopefully, fingers crossed, it's clear from context. But they're defining the mean vector to be a vector in Rn, all of whose components are x bar, where x bar is defined over here. If we look at the norm of that mean vector, the norm of the vector with all the x bars in it, norm squared, we'll square the entries, add them up. Hey, there's n entries. It's a vector in Rn, it says right there. So we'll get n times x bar squared for the norm of that vector. And yeah, I'm distressed that x bar is used both for the entries of that vector as well as the vector itself. We'll be careful with that when we go through and use this, if we do encounter very much of this. But me complaining about some of the notation in the book, again, get used to it. You ain't heard the last of it. And that brings to an end section 2.1. All right, next section has less proofs. It's also quite a lengthy section, and we're still in a process mostly of reviewing ideas from sophomore linear algebra. This equivalence of norms thing, that's certainly something new to you, I suspect, though. I will see you in section 2.2.